Um, okay, let's get started. My name is Yifan. I'm a PhD candidate working in the Optical Sensing Lab here at NC State University. My advisor is Dr. Michael Kutnov, and we do a lot of works in building optical sensor systems used for different agriculture projects using computer vision. And I'll be introducing some of our collective works done by me and mostly graduate members in our lab in the sweet potato production industry. This is a very big project that's been going on for years. I'll start with some introduction in the sweet potato industry. North Carolina is the number one sweet potato producing state in the US since 1971, and it goes through a production process from the growing fields to our dinner tables. And consumers usually prefer produce that's appealing on the outside rather than the nutrition contents. People go to grocery stores and tend to pick the good-looking ones rather than the wonky ones, right? And sweet potatoes come in very different shapes. For example, we got these beautiful ones that's on the left here that are perfect in size and shape. We also got this like giant one in the middle here, and these wonky ones with damages and defects. But you rarely see these ones in the grocery stores like Walmart, Trader Joe's. That's because those were already picked out during packing and sorting process in the production pipeline. Sorting sweet potatoes are very labor intensive. It relies on experienced workers standing at the production lines and sort sweet potatoes one by one. This is called sweet potato grading, which relies on visually checking the size, shape, weights, and defects or damages for each individual sweet potato. We are talking about hundreds of sweet potatoes being processed every minute on an actual production line. And after grading, the sorted potatoes are then packed into boxes and ready to ship to grocery stores. These big retailers usually order from packers by boxes of different grades of sweet potato. For example, Walmart can order, let's say, 40 boxes of US number ones, which is the best looking sweet potato grade, 20 boxes of these giant ones, and 10 boxes of the tiny ones. But the packers don't have this real-time production information to know the yields until after all the sweet potatoes are being processed and packed. So fulfilling different orders are actually a very challenging task. It relies on experienced experts to kind of predict when and how each order could be fulfilled by knowing each grower's production information in the past years. So a detailed yield estimation is especially important for packing facilities to match their inventory and yields to different orders. And on top of that, once the sweet potatoes are washed, they cannot go back to storage. Luckily, with sensing technology and AI getting more and more popular in pretty much all the fields right now, we can develop sensor devices and collect objective data from packing lines for information gathering. And we can also use computational approaches to monitor and analyze the data to help sweet potatoes packing facilities solving these problems and challenges so that they can optimize their day-to-day operations by leveraging the power of data to help packers decide what and when to pack sweet potatoes to reduce waste. In this presentation, I'll introduce some of the works we did to develop sensor and computing systems that are already deployed in several packing facilities across North Carolina. They're constantly running computer vision and AI algorithms to automatically grade each individual sweet potato from the collected image data, and also estimate real-time yield information to help packers gain production insights. And we developed camera and edge computing systems to three different production stages. The first one is a portable system built based on a smartphone. It does in-field estimation in real time during harvesting. This happens in every grower's fields before the harvested sweet potatoes are transported to packing facilities. It gives the growers yield estimation right there in the fields instead of the traditional way that will have to wait until after all the sweet potatoes are processed and packed. The second system is called the top bin system that are installed at packing facilities. It basically looks at the incoming trucks loaded with harvested sweet potatoes from above during the receiving stage, but before the sweet potatoes are being dumped onto packing lines. And in the third approach, we install several camera and computer systems at different parts of the packing lines during conveyance stage to monitor production and also track incoming sweet potato information related to different growers. Starting from the first system, we're using a Google Pixel smartphone to capture images in the fields during harvesting. And we trained a custom a mask RCNN based instance segmentation model to extract masks of each sweet potato and perform grading matrix estimation. A smartphone does not typically have a lot of computing power, so we deployed a lightweight mask RCNN model to the smartphone and only run inference during harvesting. The model was built using a ResNet 50 based model, which is trained using the COCO dataset. We then transfer learned the model using our own manually annotated dataset. The extracted masks are then being used to estimate the grade metrics, such as length, diameter, and we'll also further estimate the volume and the weights from the calculated size metrics. During the development phase, we also did a model validation from individual sweep data level and also from a whole picture level to ensure the volumetric estimation is accurate. We also collected testing images in the lab to reconstruct 3D shape of the sweet potatoes from multiple images to calibrate the weight estimation. Uh, Overall, we were able to achieve root mean square error of 0.66 centimeters in length, 1.22 centimeters in diameter, and 74.73 grams in weight, which is able to give reasonable yield estimation to growers that were traditionally unavailable. And after harvesting, the other two approaches are we developed are for post-harvest production. The systems are deployed at the transportation and also the conveyance stages, respectively. These stages are in the packing facilities after all the harvested sweet potatoes are being transported there. Um, this is the top bin system. Um, which looks at the basically the top layer of sweet potatoes loaded on trucks when they are being transported to packing facilities. It consists of a portable trailer equipped with a pole that extends to 5.5 meters high. A beam attached to it spans about 3.6 meters from the base. And the sensor system is actually installed here on this beam, looking downward. This structure allows the transportation trucks to drive by underneath while taking images of the top layer of the sweet potatoes. We also have another camera that's installed here on the pole that looks at the side view of the trucks, scanning the barcode that's attached to the side of the bins. The text contains grower and harvest information. The cameras are also triggered by a motion sensor that's also installed here. So trucks loaded with the sweet potatoes drive by, triggers the cameras to capture grower information that's on the side of the bins, and also takes pictures of the top view of the sweet potatoes for yield estimation. And we're using the same mask RCNN model, similar to the one discussed before. And here we estimate the same grading metrics, length, diameter, shape, weight, and from the extracted masks. Other systems are all deployed around the conveyance stage of the production line. This diagram shows an overview of that conveyance stage. So the sweet potatoes are being dumped into the dump tank, where they get washed and then moving on to the eliminator table, where all the unwanted ones gets eliminated from the packing line. The rest will move on to the rest of the sorting line to be graded and packed based on different grade categories. We installed a camera system at the dump tank that we call track and trace system. It looks at the information tag attached to the sweet potato bins for grower information. We also installed another camera and computer system at the eliminator table to monitor the basically the total input. Another camera installed to capture the waistline. We also have a separate system that looks at the US number one sorting line to capture basically their best product. Starting from what we call the Eliminator system, which is installed on top of the Eliminator table, which is basically a rolling conveyor belt after all the sweet potatoes are washed. Tiny sweet potatoes will fall through the gap between the rollers, and there are workers on both sides of this table manually picking out the waste. Um, the cameras are installed on top of the center of the eliminator table, facing downward, using this frame structure formed by vertical and horizontal metal bars. The cameras are connected to the edge computer system installed next to the table here over on the bottom right corner, this direction. The edge computer runs software pipelines to capture images and also run the same mask RCNN model inference to get masks for each individual sweet potatoes. Then calculate the grading metrics. The cameras are triggered using a magnetic hall sensor synchronized to the conveyor rotating shaft. The sampling rate of the image capturing is roughly 0.3 hertz, or another word, it takes one image every roughly 3 seconds. To avoid detecting the same sweet potatoes in the neighboring images due to the wide field of view, we only use a cross section of the image to perform instance segmentation. An example is shown on the right here after the detection. And here's another what we call a second generation Eliminator table edge system we installed at another packing facility. The hardware setup is similar to what we've seen in the previous one, but every facility has a different conveyor setup. Moving speed is different, width of the table is different. So other than switching the lens on the camera, most difference in the software pipeline setup. For example, we need to tune the region of interest. Um, to when feeding the input images to the mask RCNN model for inference, we need to capture the entire cross section of the table and also remove the duplicate in the neighboring images to avoid double counting sweet potatoes on the edge of the images we can see here. Another important factor is the size estimation parameters, where we need to modify based on the physical dimensions of the eliminator table. And diving more into the sensor and edge computing systems building, each facility has a different setup, so we need to custom build each system to fit the facility specific requirements or constraints. On the left here is our first generation system. We have a regular desktop computer with a GPU in there, along with ready-to-use power supplies. The electronics on the top here runs the cameras and the LED flash. And in the second generation computer system in the middle here, this is a much more compact system and also a much cheaper system. We have a desktop motherboard in there, along with an onboard GPU, along with other electronics to power the different components. And on the right side is the actual camera box we built. There's a RGB camera and also a polarization camera in there. RGB camera images are used for the mask RCN instance segmentation we saw earlier, and polarization cameras only allows a certain oscillation direction of the light wave to reach the sensor, which allows a better visual signal for certain material properties. And in our case, skin blemishes on sweet potatoes are much more visible from polarization images. The polarization camera needs a LED flashes at a specific wavelength. All these electronics on the left side here is the driver that runs the LED, and that's also synchronized to image capture. And all these enclosure boxes are water resistant because when the production line is running, there will be constant water and mud splashes. And the humidity is really high during operation, especially during hot summers we have here in North Carolina. So all these connectors going in and out of the boxes are industry level water resistant connectors, which means we'll have to make our own cables and wires to be able to fit inside the box and also compatible with the connectors. After installation of these systems, software pipeline setup will be the next step. Although the inference model is the same, we need to configure the image capture and the data ingress pipeline for input and output handling. And we chose to go with the edge computing approach mainly because of the data privacy and network connectivity issue. The production information is key to each packing facility, and they are the owners of the collected data. So keeping data on the edge is very important to ensure their data security. Additionally, these packing facilities are usually in a remote location. The stability of internet can sometimes be an issue. So instead of transferring large amount of image data to a centralized server, edge computers reduces delay and also avoid losing data during internet interruptions. Um, Next system is deployed to capture the waste using a RGB camera that connects to the computer system we saw earlier. We collect these waste images to estimate how much waste they're producing, and this is part of the production information that packers look at. And the next system is what we call the US number one system. And US number one is the most important and also the most profitable grade for packers and growers. And here we built probably going to be our third generation system that is much cheaper and compact than the Eliminator system we saw earlier. And instead of the two boxes, one for computer and one for the cameras, this is a kind of all-in-one system that has a powerful system on chip device with a RTX 3050 low-profile GPU to run the same instance segmentation model and calculate the grading metrics. We also have a Raspberry Pi in the box that runs a global shutter camera and it's also triggered using the magnetic hall sensor that's synchronized to the conveyor belt. And even though the entire system is much more cost effective, the inference performance is comparable. Okay. The inference performance is comparable to the bigger Eliminator system with a full computer. And here we also have some examples of the masked RCNN results for the detection of the US number one products. And going back to the dump tank at the beginning of the conveyance stage where all the sweet potatoes are washed, we installed another camera at the ceiling of this, above this tank. looking downward when the workers are dumping sweet potatoes into this tank. We aim to capture these tags attached to the bins for grower and harvest information from the tag. We call it track and trace system. These tags contains information about growers, where the sweet potatoes came from, along with the yield estimation. The packers can have information like this grower produced this amount of US number ones, and this amount of giants, and this amount of the tiny sweet potatoes. And it also completes the information gathering circle from input to output. And okay, that's a lot of hardware building. After processing the image data on the edge, we also built a online dashboard to receive the results and show users production information. The users here would be mostly be packing facility staff. The dashboard allows the users to view their real-time production information, such as weight counts for each grade category and how much product they're produced. There's also a function to view historical data from a given time range. For example, the users can see how much sweet potato of each grade they've produced during the last week or during the past year. The operation tabs allows the users to see the current status of the systems. Like, are there any systems that are offline, and how long have they been offline for? This orders tool allows the users to see what the current active orders are and how to best fulfill these orders based on the current yields. And this data drift tool gives the users the ability to customize size profiles from different customers. It basically pulls the real-time production information based on the customized size profile and regenerate the distribution that's already produced. And here's a quick summary of how sensor systems and computational methods we developed are being used in sweet potato production industry to capture traditionally unavailable data and generate business insights for different stakeholders to inform their decision makings. Therefore, leading to reduced waste during production and also increased profitability. And here's our contact information and our lab website if you're interested in what we do. Feel free to reach out if you're interested or have any other questions, and I can take some questions.